Okay, we've been talking about the wonderful world of titrations here. And last time we talked about a couple titration curves. We talked about our strong acid and strong base titration. And you did one last time as well. So we have this titration curve where we have the volume of sodium hydroxide added, for example, and our pH. And looks a little not deal. And again, here we are adding our sodium hydroxide, say, to like a strong acid like HCl. And remember that pretty much this is what a titration curve looks like. And pretty much all titration curves have a kind of four important parts to the titration curve. We'll throw our equivalence point right about there. We have in this particular one, really at the very beginning, and at the very beginning of this type of titration, as we talked about, pretty much that is all you have in your beaker or your flask or whatever you're doing. And that is a strong acid, which means pretty much you could go right into the pH equation with the concentration of the strong acid. In most cases, that concentration of strong acid is going to also be the concentration of the H plus because it's monoprotic, and you can go right in there. Once we do start sort of dropping the first drop there of our base in this case, kind of brings us to our second part of the titration curve, which is pretty much from the first drop to before the equivalence point. We are going to obviously get a reaction that's going to occur. That will require you to do, thank you, one ice table. And again, this ice table, as we've talked about, does need to be done in moles since we are adding volume. Once you do that, what should really happen is, in this case, the amount of base that you're adding will be the limiting reagent and get all used up. You'll have basically some strong acid left over. So really the point of this ice table is to figure out the concentration of your strong acid after it reacts with the amount of base that you added at that point. Once you do that, ice table and moles, as we talked about, you should always sort of get into the habit of converting it back to molarity after that first ice table using the total volume. Once you do that, you still have a strong acid, which means you can go into your pH equation at that point, which is minus the log of the H plus concentration. In this type of titration, as we talked about, when we hit that equivalence point, that is the definition of basically the moles of the acid will equal the moles of the base. And in this type of titration, what you'll basically have is all of the acid and base that you started with and added will get completely used up. And really, the only thing that you'll have left over at this sort of third point is you will have a salt left over. And that salt would have come from a strong acid and a strong base, which means we know that that salt should be a neutral salt, which means really there's not much calculation that you should have to do in this type of titration at the equivalence point. We would expect it to be neutral because, again, the only thing left over at that point is a neutral salt. Lastly, going past the equivalence point, which might have been nice for some of you after doing other titrations. And at this point, you're really just sort of adding more base than you need. You're really adding an excess amount of base. And that does require an ice table to be done at this point. And the purpose of this ice table really is to figure out how much of the strong base that you've now added to it. Because at this point, remember that when you look at your ice table, whatever you are starting with, if the moles of what you're adding is less, you're before the equivalence point. If they're equal, they're at the equivalence point. And then if you're past the equivalence point, whatever you're adding should have more moles than what you started with. And that would mean that your acid in this case would be the limiting reagent. So the purpose of this ice table would be to actually figure out the concentration of your strong base you would have left over at this point. That will give you really the OH minus concentration, which will allow you to get to the POH and then to the pH. So again, depending on where you are in sort of the titration curve, this is pretty much how it's going to end up in terms of the pH. And again, what we just talked about here, as we talked about last time, is specific for this type of titration. Now, any question on that? before we go on that. Okay. So we also talked about another type of titration, which was a weak acid with a strong base. And it's sort of the same setup here. We're going to have our base up here in the burette. We're going to have our, bless you, our weak acid there in the beaker. And again, we're going to be adding base to our acid. We will get a titration curve that will look very similar. It'll look something like this. And we'll have a little equivalence point here. And in this titration curve as well, there's still really those same four spots that you want to think about. We have, again, our first spot here, which is before we begin. And in this first spot, though, it is a little bit different than the previous titration. We are actually starting with a weak acid in this case. So this is really a Ka type problem. You need to do an ice table. You could use molarity and X's, and obviously solve for X. And when you solve for X, that will be your H plus concentration, and then you could get to your pH using the pH equation to do so. Now, when we start our titration from that first drop to before the equivalence point there, once again, this will require you to do an ice table. This ice table, once again, should be done in moles because we're definitely adding volume at this point. What's going to happen at the end of this ice table is you will hit our favorite thing, which is a buffer, pretty much, as we talked about. You will hit, really, in most cases, an acidic buffer at this point. And that means you really have two options as to how to get to the pH. You could either do another ice table and sort of a common ion type ice table, or you could use the Henderson-Hasselbalch. And I would say probably the Henderson-Hasselbalch equation there, if I could write it correctly here, would be probably the easier choice of the two, but you could, again, lay up an ice table. Once again, like normal, I would definitely highly recommend converting back to molarity after that first ice table. And again, just kind of puts you in the right units for other things along the way. The third part of titration here is the equivalence point, and you will need an ice table, and you will be left off here with a salt. The difference is, though, we have a salt that's coming from a weak acid, which means it will go through hydrolysis, which means you will need a second ice table. And that's going to be a hydrolysis type problem. And again, probably a little swapping out of some K values and things like that. And again, it will probably be basic in this case because this comes from a weak acid, which means the salt will act as a base and it will accept an H plus from water, and it will produce hydroxide. And you should expect the equivalence point here to be basic in this type of titration. That leaves us kind of similar to the last one there. Past the equivalence point, you do need an ice table. You will actually have in this one two things left over. You'll have that same salt, and you will have basically a strong base left over. Once again, as we talked about in this part of the titration curve, because the salt will go through hydrolysis and produce hydroxide and really act as a base. At this point in the titration, though, it is that strong base that's going to be the major contributor to the OH minus that's going into that solution. And that's frankly because you're sitting there with your burette and opening it up and just dropping hydroxide in basically at this point. And that's going to be your major contributor there. So typically speaking, at this point in the titration curve, we ignore any sort of contribution from the salt, as that hydroxide coming from the strong base will be your major source of hydroxide, which means you essentially will have the hydroxide concentration, and that means you could go to your POH and then to your pH. So although it is sort of the same four spots here along this titration curve, it is a little bit different depending on, you know, the type of acid and base that you are titrating. Any questions on any of those? I think we also talked about it as well, that it's good to, again, have an idea as to what should happen in the calculation right before you begin, and kind of know where you're at. All right, so I think we went through the different parts of this one. but I don't think we did an example. So why don't we throw an example out here and see how we do? Let's do, I don't know, let's say we want to know what is the pH when 21 point, why not? We'll go 3. Everybody can do 5. We'll do 3. I very badly written 3. Milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar acetic acid in a titration, huh? The Ka value there for acetic acid, the classic 1.8 times 10 to the minus 5. Also, I think we will need to get some moles of everybody, and we'll also need to do an ice table. So we'll do our moles here first of our sodium hydroxide. Once again, we got to convert our volume there into liters. We're going to use the molarity of our sodium hydroxide, which is 0.1 moles per liter. And we will go with 0.1 times 0.0213. And that's going to give us 0.00213 moles of sodium hydroxide. We will also need our moles of acetic acid here, and we'll do the same thing. We will convert our volume into liters. We will use our molarity here of our acetic acid. Liters will cancel, and again, here, a couple of zeros and a 2.5 there. Questions on that so far? All right, so we need our reactions. So in this case, a little bit of that there. We have our sodium hydroxide plus our acetic acid. A little double displacement action happening here. Going to give us some sodium, not sulfate, sodium acetate would be a better way to say that, I suppose. And a little bit of H2O action happening here. Clearly, as we talked about, we're going to do this in moles. And we'll take the moles that we just calculated there, 0.00213. 0.0025 and 0. Again, this is what I'm adding. That is what I'm starting with. So my question is, am I before, am I at, or am I after the equivalence point here? I am before the equivalence point, as the moles of what I'm adding is less than the moles of what I started with. So again, if we were equal, we would be at the equivalence point. But since what I'm adding is less, we are definitely before the equivalence point in this part of the titration. That also means that, as we can see from the numbers, the limiting reagent here is going to be our sodium hydroxide, as that is the smaller number there. So we're going to use up all of our sodium hydroxide here. And a little plus action. And that means at equilibrium, we would expect to use up all of our sodium hydroxide. We would go 0.0025 minus 0.00213. Going to give us 0.00037 moles of the acetic acid, 0.00213 moles here of our sodium acetate. Once again, at this point, what we're going to do is we're going to figure out our total volume, so we can convert these back to molarity, which is a really good idea. At this point, we started with 25. We added in there 21.3, and that's going to give us a 46.3 milliliters as our total volume. Remember, that does need to be converted back to liters as well. 0.0463 liters. We're going to divide everybody by here. And if I can grab my calculator out. 3 zeros there. 0.0463. Going to give us a 0.00799 molar for the acetic acid. 0.00213 divided by 0.0463. Going to get us a 0.0460 molar there for our acetate. First off, any questions on the ice table or anything so far here? Once again, if you are not sure what should be happening at this point, which, by the way, you should be sure of because you know where you're at, but you could use your ice table to figure out what we got going on. I have a little sodium acetate left over. I got me some acetic acid left over. These two things are related to each other, yes or no? Are they related? They are. They are what? They are a buffer, which is exactly what we should have predicted, right? Before we even did the calculation here. So again, it's a good idea to take that moment and think about where you are in the titration curve to just make sure your calculation comes out like it should. This now means that we do have two options to solve this. We could either ice table it, or again, I would say probably the Henderson-Hasselbalch would be a probably easier choice. That's what I'm going to do. I'm going to use the Henderson-Hasselbalch here. Plus, I'll make that a big plus sign, log of the base over the acid. The pKa value in this case minus the log of the Ka, which would be minus the log 1.8 times 10 to the minus 5, gives us 4.74. That means that my pH here will be 4.74 plus the log. Again, this is our base, which would be 0.0460. That is acetic acid on the left there, which definitely should be our acid. I think that's 99 actually. 99. And if we do that there, we will take our base divided by our acid, a log, and a 4.74. Going to give us a pH here of 5.50 in this case. Yes. Once again, if you chose to do a second ice table, a Ka type table with acetic acid, remember you need the sodium acetate in the initial part of that table. Otherwise, you're not really doing, again, the buffer part of the calculation. As we can see there, 21.3 is in this ballpark. That's not bad. I would say we probably did all right there. It's about where we're at. Any questions on any part of that calculation there? So again, it's really important to make sure you understand where you're at, so you understand if you are doing the correct calculation. You don't want to do some wrong calculation. As I did mention before, if you do choose to use the Henderson-Hasselbalch, technically speaking, if you use the moles here, it will work out the same because the volumes will cancel. But again, just good practice. In other spots, you will need molarity. So it's just a good idea to swap it to molarity, even though really, if you use the Henderson-Hasselbalch with the moles, it'll come out the same. Other questions like that? All right, so that is weak acid, strong base. So let's talk about the third type of titration we're going to talk about, which is a strong acid and a weak base titration, something like that. So in this case, we take hydrochloric acid, which is a strong acid, and NH3, which is a weak base. And in this particular case, it is a little bit different. The acid, or the HCl, is actually up in the burette, and we're adding acid to our base in this case. That is why when you look at this titration curve, it looks upside down, because we are actually starting with a base. So we have a high pH to start with, and we're adding acid, which means the pH is coming down. So instead of like the previous ones where it went kind of up, we are basically starting high and coming low here as we continue to add acid in this particular case. Probably no surprise here. There are still the same 4 spots on this titration curve that are on pretty much all the titration curves. So the very first would be obviously before, in this case, we added any acid. Second would be after we start adding acid until we reach the equivalence point. Our third stop along our titration tour here will be the equivalence point, and our fourth journey here will take us once again here past the equivalence point. So we're going to go through each of these parts like we did on the other ones and just kind of think about the calculations and think about what we end up with and, what we should expect to happen. So let us start here with step number 1 there, which is before we add any HCl. So in this case, before we add any HCl, really the only thing we have in there is NH3, and that is a weak base. Yeah. Which means to figure out the pH of a weak base, I need an ice table. Yeah. And this can be done in molarity as we have not added any HCl to it. So, this would be something like NH3 plus some water, right? This is going to be a base, which means it's going to accept it. Going to make a little NH4 plus and a little OH minus. You could also keep those guys together if you like. You'd use your initial with molarity, some zeros, some minus X's, some plus X's happening there. A little minus X, X, and X. This clearly would go into our KB expression. We would solve for X. It is important, though, to remember, though, that when I do solve for X in this case, what does X equal in terms of the pH? That actually equals the OH minus in this case, yeah? So that will give you your OH minus, which means you're going to probably get your POH first and then to your pH. So you got to remember, again, unlike the previous titration where we had a weak acid and we solve for X, that's going to be our H plus concentration. Here we are going to get the OH minus concentration, which means we have to go through the POH first and then to the pH. It is very similar to the last titration, except obviously you're dealing with a weak base versus a weak acid, but really kind of very similar in terms of the type of calculation that you have to do. Any questions on that one there? All right. So let's talk about what happens once we really kind of get into the titration. So once again, in this case, we are adding acid here to our base. So we're going to start to add our acid, and we're going to start to see, as we kind of saw a rise in the pH before, we're going to start to see a decrease in the pH as we continue to add acid. So since we are adding acid, that's the second part. And before the equivalence point, we will have to do an ice table. So in this particular case, we would have HCl plus a little ammonia here. And this is going to give us some ammonium chloride. And it is up to you on this one. You can keep the ammonium chloride together as one thing. You could kind of split it off into 2 things. Maybe in this case, it would be good to keep them split off, and we'll explain why in just a second. So here, clearly, we are adding this guy, and we are starting with this guy. So once again, here, we should do this ice table like we've done in previous titrations in moles. So I'm going to, once again, just make up my moles of starting amounts. So I'm going to start with here 4 moles of ammonia. And if I am before the equivalence point, the moles of my hydrochloric acid should be less than, equal to, or greater than 4. It should be less than, right? Because we're not at 4, which would be the equivalence point. So once again, I'm just going to make up 2, and we have 0 here. Change is going to be -2, -2 plus 2 moles. That means at equilibrium, I'm going to have 0 there. I'm going to have 2 moles of this guy, 2 moles of this guy, which you then can convert back into molarity by using the total volume like we did before. The question is, why am I not writing anything here under chloride? What is chloride? What type of salt is that? Will it affect the pH? It will not. It's a neutral salt, right? So no sense putting numbers where you don't really need to use them, right? So if you could obviously recognize chloride as being neutral, and no sense of putting anything there, right? If you did, you just need to recognize that at the end that you don't really need to use it for anything. So this is pretty much neutral, right? So we're not going to kind of put anything there. That means that when we look at this ice table, we can now clearly see the two things we have left over are these two things. Are these two things related to each other? They are, yes. That is a weak base and its conjugate acid, also known as a buffer. Yeah. So just like the previous titration, you are going to hit a buffer in this case before the equivalence point of this titration. The difference is between the last titration, the weak acid and strong base, and this one, which is our strong acid and weak base titration, is most of the time here before you reach the equivalence point, there will be a basic buffer. You just hit basically a basic buffer at this point. So really at this point, you'll have a buffer, which means to get to your pH, our friend, the little David Hasselhoff equation here happening, pH is equal to pKa plus the log of the base over the acid. Remember, although it is a basic buffer and you probably have the Kb given to you, you could still use obviously the Henderson-Hasselbalch. You could convert the Kb into Ka. You can convert the Kb into pKb and subtract 14 to get to the pKa. You can do all those things, whichever way you want to do it. You could also do an ice table here, and you actually have two versions of the ice table that you could do if you wanted to. You could do like a Kb type ice table with NH3 and NH4 on the right, or you could do a Ka type ice table with NH4 plus on the left and NH3 on the right. So there are various ways you could get to the pH here. Probably the simplest and easiest straightforward way would be the Henderson-Hasselbalch sort of move at this point. Any questions on this? So again, much like the last one, before the equivalence point, you're basically going to make a buffer, which is essentially what happened here. We reacted a weak base with a strong acid, and we actually made an actual buffer through that reaction. Just like the buffer we talked about in the previous titration, at some point as you continuously add HCl, you're going to blow through that buffer, and that's where we're going to see our big drop, right? Right about here, you're going to blow through your buffer, and we're now going to have a pretty big drop to our equivalence point because at this point, you kind of blew through the buffer action. That's why, again, we don't have such a giant steepage drop, but eventually you'll kind of break through it and it will drop there. And that will bring us to the third part of this titration, which is the equivalence point, right? And at the equivalence point, that is still where the moles of the acid should equal the moles of the base. And clearly we will still have our reaction here, our HCl plus our ammonia, making a little NH4 plus and Cl minus, that's it. I think I remember. All right, so adding, and that is what we're starting with in this case. So once again, if we take our made up 4 moles, clearly because we're at the equivalence point, we should have an identical number of moles of the HCl that we're adding. And as we talked about last time, remember that there are also many different ways you could figure out the volume to reach the equivalence point if it is not given to you. So if it is a one-to-one relationship, you can use M1V1 equals M2V2. If you don't have that, but you know the molarity of your HCl in this case, you'll know how many moles you should have. you know the molarity in the moles, you could just use the molarity formula to figure out the volume that would be. So again, there are many ways that you can figure out the volume if you need to. Once again, here we're going to have none of this. The good news is at this point, you can't really hopefully pick the wrong number since there's only one number to pick, and that would be the 4 in this example. That's going to mean nothing happening there, nothing happening there. A little 4 moles here, along with my converting back into molarity using the total volume. Once again, I can recognize off the bat here that the Cl minus is again going to be neutral, so I'm not going to do anything with it. At this point, though, we are left here with just this guy. And NH4 plus is a salt, right? And it's basically ammonium chloride is the salt. But the NH4 plus part is the important part of the salt here because that came from a weak base, which means it will go through hydrolysis. So much like the other titration, you will have a hydrolysis situation happening here at the equivalence point, which means because this is a weak base and that's where it comes from, that is going to be as conjugate acid, which means when it reacts with water in this case, it will act as an acid, which means it's going to actually send the H plus over here. That's going to give me NH3, which you always get where it comes from, and a little H3O plus in this case. By the way, at this point, the solution should be acidic, basic, or neutral. The solution here should be, I'm just going to keep circling it. It's going to be, I'm going to circle it the other way. It is going to be acidic, yes, because we are producing H3O plus. So we should know that we should hit an acidic equivalence point because we will have a salt that will go through hydrolysis and create H plus. We also know that when we do this ice table, which I'm going to tell you we have to do, what type of K value should we be using? Ka. You most likely will have a KB given to you. So here again, that KW, Ka times KB situation happening. Our second ice table, which you need to do, we're going to take our equilibrium of the first ice table, and that's going to become our initial here. So this guy is going to become our initial here. The rest of this table is just going to be x's, so zeros, minus x, plus x, plus x, initial, minus x, x, and x. This is going to go into obviously our Ka, as we talked about. We will solve for x. In this case, though, x does equal the H plus concentrations. So in this case, when we do solve for x, that will be our H plus concentration, which means we could directly go into our pH at that point formula and calculate the pH. So we would expect the equivalence point here in this type of titration to be acidic, as we will always be producing a salt through hydrolysis, and that salt will always be producing H plus. And that is very similar to what happens in the weak acid strong base titration. The difference is we create a salt that will go through hydrolysis and create hydroxide, which will give us a more basic at the equivalence point. So we talked about 3 different types of titration so far. And at the equivalence point, we do expect the pH to be different depending on the type of titration. Strong acid, strong base, because we have a salt that is a neutral salt, we expect the pH at the equivalence point to be 7. In a weak acid, strong base titration, because we create a salt that will go through hydrolysis and create hydroxide, we expect the pH to be more basic at the equivalence point. And in this type of titration, when we reach that equivalence point, we will still have a salt that will go through hydrolysis, but it's going to create H3O plus, which means we expect it to be acidic. So as you're doing your titrations today with a weak acid and strong base, you should expect your equivalence point to be more basic, higher than 7, right? Is where the equivalence one should be. Any questions on the equivalence point there? Yeah. Yeah, so pretty much in titrations here, and specifically the last two titrations, this one and the one previously, we will only really hit a hydrolysis situation because at the equivalence point, the definition basically means all the acid, all the base you're playing with and sort of adding is gone. So the only thing we're left with at the equivalence point is a salt at any equivalence point in a titration of an acid and base. But the case of these last two titrations, the salt that we're left with is a relatively strong salt that will go through hydrolysis and will continue to react with water. And that's going to affect the pH, as we talked about with salts, because in one case, it's going to create more OH minuses, which is going to make it more basic. And in this case, it's going to create more H3O pluses. So that's really, again, the only point in titration where you will hit possible hydrolysis is at the equivalence point. Other questions? It should always be acidic in this type of titration. So if you're doing what we're doing here, a strong acid with a weak base titration, you should always pretty much at the equivalent point hit acidic. And as we'll see here, if you look at the actual graph, we actually hit acidic, kind of running into the equivalence point before we actually get there. So as it starts to drop, we actually do hit it acidic before we actually reach the equivalence point. So you should always sort of expect it to be acidic in that case. And that's the same idea as what we see over here. We actually run into the basic sort of thing with this type of titration before we hit that basic, technically equivalence point. And that's because in both of these situations, this type of titration where we kind of run into the basic before the equivalence point, and the one we're talking about right now where we run into the acidic before the equivalence point, it's because before those, at those points, you have a buffer that you essentially blew through. So once you blow through that kind of buffer part before the equivalence point, you get to a point where you just influx into that solution a lot of either H plus if you're adding the HCl or OH minus if you're adding the sodium hydroxide. So you see that really big jump to the equivalence point. And that's why you see typically when you're doing it, that kind of jump to the equivalence point. And then you also see it past the equivalence point as well, because at that point, you're just adding more of whatever you're adding, the HCl or like the sodium hydroxide. So again, you're just influxing a lot of that strong acid or base in those titrations. And that's why you get that big jump to the equivalence point, because you blow through a buffer and then you kind of jump afterwards, because now you're just continuously adding more of like the HCl and stuff like that. Other questions? All right, so that leaves us here, number 4, speaking of blowing right through the equivalence point. Let's talk about what happens at this stage. And as you can see here at the equivalence point, it's about a pH of 5 point something here, I think, which is definitely acidic. And so at the 4th spot after the equivalence point, we are definitely still having the same reaction. Or HCl and our ammonia in this case. Gonna give us a little NH4 plus and some Cl minus. So once again, we are starting with this guy. We are adding this guy, and we're going to do an ice table in moles. So we'll start with my 4 moles. We have now gone past the equivalence point, which means we should know that the moles of HCl in this case that we're adding should be more than what we're starting with. So I'm going to make up a number of 6. Seemed to work good last time. And 0 here. So again, just making those up. Here we do again have more moles of what we're adding than moles of what we're starting with. So there is again a kind of switch that occurs. In this case, our HCl will actually become our excess reagent, and our limiting reagent, right, is our NH3. Once again, as I talked about before, always take the smaller number if you'd like to get it correct. Yes, so always take the smaller number when you have that option. And again, it's usually around this point when people doubt themselves and try to take some weird numbers or not sure what to do. So here we'll go -4, as that's going to be our limiting, and +4 here. We will end up with 2 moles of that, 0 of that guy, 4 moles of this guy. We're going to do our normal proper procedure here, take the total volume and convert it back to molarity here. So we are definitely past the equivalence point. We have these two things here. Is that a buffer? It is not a buffer, and as I mentioned, I think a number of times, just because you have two numbers, it doesn't make it a buffer, right? So these things are not really related to each other. So we have the two things that we saw previously in the last titration. We still have our salt here, which is acting like an acid and going through hydrolysis. We also have HCl, which is a strong acid. And much like what we did in the previous titration, if you had to venture a guess at this point, which one should be the major contributor of H plus in this case? It is going to be HCl or the strong acid. Once again, this guy's got to do a little hydrolysis. It's definitely not going to be anywhere near what you are continuously doing at this point, which is opening up your burette and just letting that stuff drip in, right? And as soon as it hits every time, you're going to have a lot of H plus. Like you might see your pH meter, right? And maybe it jumps really high. For example, in your case, you're having sodium hydroxide. When you drop it in there, that's because it hits it, right? And it shoots up really, really high. In this case, by just adding the HCl, we're adding a lot more H plus. And out of the two, we will not worry about this contribution. We are still not worried about the chloride here. So really, this is a strong acid, which means that is the H plus concentration. And that is going to get us to our pH equation at this point. So this type of titration is a little bit different, but very similar to the weak acid strong base titration. At the same four spots along the way in this titration curve, you have pretty much the exact same four types of problems. At the beginning of this titration curve, you have a weak base problem because you're starting with a weak base. So that's again one ice table in molarity, and get X, and X will be your OH minus concentration, and that will allow you to get to the POH and then to the pH. Before the equivalence point requires at least one ice table. Really, the purpose of that ice table is to figure out the concentration of the buffer you just made. And once you have the concentration of the buffer before the equivalence point, you could go into the Henderson-Hasselbalch, or your choice, you can do another ice table. At the third step requires a minimum of two ice tables. The first ice table is really just to figure out the concentration of the salt that you should have left over. The second ice table should be a hydrolysis ice table, where again, you're probably going to need to swap out some K values there for the right ones. And lastly, just fourth step here, much like the last one, will require at least one ice table. The purpose of that ice table is to figure out how much strong acid you've been adding to it, the concentration of it. That will give you your H plus concentration, and that will then give you your pH in that case. Question on that there. All right, so let's try one of these. Why not? Let's do, I don't know, let's do 29. What is the pH after 29 milliliters of, we'll do 0.1 molar HCl is added to 25 milliliters of 0.1 molar ammonia? The Kb value for ammonia is, we'll go with 1.8 times 10 to the minus 5. I just like that number. Why not? All right, so give it a go. I will as well. We'll hope for the best here. Hope. We know we need some moles of everybody, so we'll do that first here. Some moles of our HCl. Once again, converting our volume into liters, times it by the molarity of our HCl, 0.1 moles per liter. It's going to give us there 0.0029 moles of HCl. We also will need our moles of our ammonia in this case. 0.025 liters times our molarity, also 0.1 moles per liter. Gonna get us there 0.0025 moles of NH3. So we're going to get our reaction here of our HCl. And clearly, as we just calculated there, we do need to do this table here in moles. So initially, HCl there, 0.0029 moles, 0.0025 moles of this, and 0 that. Once again, that is what I'm starting with. That is what I'm adding. Am I before, am I at, or am I after the equivalence point? I am after. Again, the moles of what I'm adding is more than the moles what I started with, so I am after the equivalence point. That should tell me a couple things, but we will talk about that here in just a second. But first, it should tell us that this is now going to be our limiting reagent because we got the part where we're just adding excess amount, right, of HCl. So our change here is going to always be, once again, just want to logically think about it, the smaller number. Yeah, so you do not get a negative number. So that is going to get us here for our HCl 0.0029 minus 0.0025, 0.0004 moles, nothing there. 0.0025 moles. Total volume at this point, we started with 25 mils. We added 29, and that gives you something. 454 sounds good. So we're going to convert everybody back into molarity here by dividing by our total volume. And that will get us 0.0004 divided 0.054, 0.0074, 07, we'll go extra digit, 0.0025 divided by 0.054, 0.046296. A lot of numbers. All right, so really, if we take a look at our ice table here to try to figure out what's going on, and again, not worried about that guy. We have this guy and this guy. Is this a buffer? This is not a buffer, right? Because we are past the equivalence point, which means we should not have a buffer. We are doing what at this point? We're just adding more strong acid, right? So this is the point of the titration where we should know we're not going to be concerned with this because we're past the equivalence point, and we pretty much have just a strong acid left over, which essentially means this should be our H plus concentration since that's HCl. And that means we could go into our pH or H plus, and that would be minus the log of 0.007407. Where's that there? There it is, 0.007407. And that means what we should expect since we are just dumping in acid at this point. We have an acidic pH. So once again, if you have a basic pH at this point, something went wrong for sure. Yeah. And we'll see how we did there. We're at 29. Where are we at there? 29 is somewhere on this particular titration, which I think is this one. That's right about between those two, I think. So it's not too bad. Any questions on this titration problem here? So again, it is good to know where you're at because knowing beforehand that you're after the equivalence point should allow you to know that there is no buffer after the equivalence point ever, and you should not be doing any type of buffer calculation. So again, these are the things that sometimes people just blow by. They just try to do the calculation, try to figure it out as they're going through it. It's good to take that moment and sort of think about where you're at. As I mentioned last time, you should really know the calculation you should be doing before you actually do it. And it just makes it a lot easier, hopefully, and avoid some mistakes. Any questions on any of these three types of titrations? You need to be able to calculate the pH anywhere along these curves or a bunch of points along these curves. Yeah. Any questions on that? Okay. So this is an example which you will do at home and bring back on Thursday, and we'll go over it together since clearly we do not have time to do all 4 parts of this. So these are 4 different parts along a titration that you need to do and figure out the pH at each of these steps. So please work it out before you come, and not to start on Thursday. We will work them out together, and that way you could check yourself rather than, just copy me doing it. Yes, so try it before you get here. So we're going to finish up, though, the rest of the chapter here, which is just a little conversation. We sort of had this conversation previously with the experiments, but we're going to talk a little bit about acid and base indicators. And as we talked about, acid-base indicators are typically, those indicators are kind of like weak acids. So they have a protonated form where they have basically a hydrogen on it, or H+, and IN here means indicator. And they have really sort of a deprotonated form, like the H+ has obviously come off. And really the ratio in your solution of the protonated form of the indicator to the deprotonated form of the indicator will give you really the color that you typically will see. So if it's kind of greater than or equal to 10, the protonated form to the deprotonated form, then the acid part will basically predominate. Since you could kind of think of this as like the acid part of the indicator, and this is like the base part of the indicator. And vice versa, if we have really more base part of the indicator in the solution than the acid part of the indicator, it'll give you that. As we talked about, for the most part, our indicators work over a specific pH range, and they have different colors along the way there that they will change to and from. And the idea when you go to pick an indicator, and we had a bunch, I think, the other experiment that we did there, there's like crystal violet, which is kind of yellow to begin with, kind of rolls into a little bit of green and then some blue. We have bromocreosol green, which also is kind of that yellow to blue. We have our purple guy there, and we have our phenolphthalein, right, which is the secret word to spell somewhere on your exam coming up. It's colorless to pink. And you can obviously see there are some indicators to work well in basic type solutions, right? They change color. And there's some that change color in acidic type solutions. And there's some right there, like in the 7-ish range, that change color as well. So when you go to choose an indicator, the idea is to choose an indicator near that will actually change a color near your equivalence point. So you have a visual representation of, hey, maybe you should stop your titration, right? Because in a normal titration that you do, unlike the titration curves that we do, where we just kind of keep going, you usually do want to stop there at the equivalence point. It's usually most times where you want to stop. So you want that indicator to be able to actually change color to allow you to stop. So for example, if my equivalence point was like in the pH of 9 or range, would this be a good indicator to use? This would not be a good indicator to use because that's going to change color at around a pH of 2, which means all through my titration as I go to 2 to 3 to 4, I have the same color, right? So it's not going to do me any good. So again, I would want to pick somewhere, in the 9-ish range, right, where we would see that sort of color change. So not all indicators are good for every titration. You would want to really pick one out. You would be able to, since now that you are titration professionals on these calculations, you can theoretically calculate the pH of your titration, what it should be at the equivalence point, and you could have a pretty good idea as to what indicator would be a good one to choose if you really wanted, to pick a pretty good one. So why don't you do that then? Say, here's a list of indicators and their colors in acidic and basic and the pH range at which they work. Let's say we did this titration here of a little nitrous acid with some potassium hydroxide. Which indicator or indicators off of this list would be good ones to choose, perhaps? Okay, so let's take a look at it. Really, the first thing you want to think about is a couple of things that we talked about with our titration curve, right? So we saw a titration curve of a strong acid, strong base, right? Looks something like this. Equivalence point, right? What is the pH at its equivalence point in this type of titration? It is 7. I think I heard somebody whisper. Yeah, so it is 7, as we again have a salt, right? That's going to be a neutral salt, right? We also talked about a weak acid, strong base titration, which looks like this. Equivalence point in this titration would be acidic, basic, or neutral. It would actually be basic, as we will have a salt that will go through hydrolysis and produce hydroxide. And that is because the salt will act as a base, right? Because it comes from a weak acid and it will accept the H plus. And lastly, we talked about a strong acid, weak base titration. I'm going to draw it right, I hope, this way. I don't know. And the equivalence point in this titration would be acidic for the same reason. We will have a salt that will produce H3O plus because it comes from a weak base, which means it will act as an acid when it reacts with water. So what we want to identify here probably is what we're dealing with, right? So HNO2 is what type of acid? It is a weak acid, right? I know that just because it's not one of those 6 that are strong. So it's a pretty safe bet that it's going to be weak in this case. KOH is what type of base? Strong base. That means the combination I got working for me here is this one, right? And that means that I should expect the equivalence point to be basic, which means, bless you, as we go down our list of different indicators here, that clearly is not going to work, right? Because that's going to turn well acidic. That's going to also turn pretty in the acidic range. That's going to be acidic. That's still acidic. That's really acidic. Although this does technically jump into the basic range, that's at the end of the range, which means it probably turned well before that. So that's probably not a great one. This one got some basic range in it. Wouldn't be bad. This one, everybody's favorite, phenolphthalein, also would be a pretty good choice. So out of these two, or this group, these two would be perhaps an appropriate indicator to use, as you would expect the color to change in a basic range. Like I said, if you really knew the numbers of your titration here, you could actually dial it in and maybe pick a better one of the two, or maybe find a third one that maybe would work just as well. Any questions on how to pick an indicator?